Chapter 13, Problem Solving. Again, this is from Harris's 5th edition of Exploring Chemical Analysis. So we'll start with number 1. How many milliliters of 0.0500 capital M molar EDTA are required to react with 50 milliliters of a 0.0100 capital M molar calcium solution or 0.0100 molar aluminum solution? Well, EDTA reacts 1-to-1. So if we have 50 milliliters, 0.0500 liters of a calcium solution, and that calcium solution has a molarity of 0.0100 moles per 1 liter, then we need 1 mole of calcium to react with 1 mole of EDTA, and I'm running off the screen. And the molarity of my EDTA is 0.0500 capital M for moles per liter. That would give me, if we run these numbers, so 0.05 times 0.01 divided by 0.05, then we would have 0.0112 liters or 10 milliliters of this EDTA solution to react with 50 milliliters of this calcium solution. Now, because the molarity is the same and we're using the same volume of initial aliquot, so we would have the same number of moles of aluminum as we would moles of calcium, we need the same amount of EDTA because EDTA reacts 1-to-1 with any of our metal cations. Number 2, give 3 circumstances in which EDTA back titration may be necessary. Well, if the analyte precipitates without EDTA, if it reacts too slowly with EDTA, or if the analyte blocks the indicator, then we would need a back titration. Number 3, what is done in a displacement titration, and give an example. Well, a displacement titration, the analyte is going to displace the metal ion from a complex. So what that means is, let's say we have in our solution a nickel cyanide complex, and it's going to be displaced. The nickel is going to be displaced by silver because of the more favorable complexing constant. So the nickel becomes liberated, and we would then titrate that nickel with EDTA to find out how much silver was present, because the number of moles of nickel liberated would be equal to the moles of silver that removed the nickel. So that's an example of a displacement titration. Number 4, a masking agent. What is a masking agent? Well, a masking agent would be if you have a solution that has, say, more than one analyte in it or more than one cation in it. So let's say you have magnesium and iron in your solution. So we want to titrate the magnesium but not the iron. Then we would have to add something that will preferentially complex the iron. Like, let's just say it's a cyanide compound. And that masks, or it ties up the iron so that then we can titrate our magnesium with EDTA without any interference of the iron. So what is water hardness? Well, hardness is going to be the total concentration of, of alkaline earth cations in water. And I'm not really sure why that's stated here, but it is. The difference between a temporary and a permanent hardness. Well, specifically, we're talking about calcium and magnesium. So temporary hardness is due to calcium bicarbonate lost by precipitation of calcium carbonate, and permanent hardness is derived from any other salt, like calcium sulfate, that's not affected by heat. Number 6, an auxiliary complexing agent. What is an auxiliary complexing agent? That is something that's going to form a weak complex with an analyte ion. And so it keeps it in solution without interfering with the EDTA. So like ammonia will keep zinc in solution at a high pH. Otherwise, it will react with the OH in the basic solution or the alkaline solution, and it will start to precipitate out before we can measure it with EDTA. So now let's get to some more complex, I didn't mean that pun, but let's get to some calculations. A 25 milliliter sample, I can't seem to write there, 25 milliliter sample that contains Fe3 plus is treated with EDTA, and let's see, that is 10 milliliters of 0.0367 molar EDTA in order to complex all of that iron. So we have Fe EDTA plus any excess EDTA. The excess EDTA is then back titrated, and that requires 2.37 milliliters, back titrating with magnesium, of 0.0461 capital M molar. And that's going to form then a magnesium EDTA complex. So what was the original concentration of iron in solution? Well, we're going to start, now that we have our equations written out here, let's start by looking at how many moles of magnesium were required. So that's going to equal the number of moles of excess EDTA. So here I have 0.00237 capital L liter of magnesium, and that is 0.0461 capital L, moles of magnesium per liter. So now I have moles of magnesium. I need to convert that into moles of EDTA. Well, it's 1 mole magnesium for 1 mole EDTA. And I get that we have 1.09257. I'm giving you all of the digits in my calculator because we're not rounding yet. And this is moles of EDTA, but specifically this is the excess. So this is the amount found here. Now we take the total moles of EDTA we started with. So that's going to be 0.01 times 0.0367. So the total moles of EDTA we started with is 0.123367. We subtract the excess, (1.09257), and we are left with the moles of EDTA that reacted with the iron. And that's going to be 0.000257743. So in other words, 2.57743 times 10 to the negative fourth. And that's moles of EDTA, and that's also going to be equal to the moles of the iron. So we can find out, go back, the concentration of the iron in the original solution is going to be this number of moles, which is in my calculator, and I'm going to divide that by the volume, the original volume. And I get an original iron concentration of 0.0103 capital M molar. That is the original concentration of iron. Number 9, we have a 50 milliliter solution, and it contains both nickel and zinc. And we're going to treat that with 25 milliliters of 0.0452 capital M molar EDTA. And we're going to bind all the metal. So the excess unreacted EDTA required 12.4 milliliters of a 0.0123 capital M molar magnesium in order to complete the reaction. And then we have more to displace the EDTA from zinc, and we have more and we have more. So let's just stop right here. We added, this is our total EDTA that was added to this solution, this original solution, not just the zinc, but the whole solution. And Our extra EDTA required this amount of magnesium, which means the moles of this magnesium are equal to the excess moles. So let's calculate our total moles, 0.025 times 0.0452. So total EDTA added is going to be 1.13 times 10 to the negative third, and that's moles of EDTA that in total were added to that solution. I need to subtract the excess EDTA, and that's going to be equal to these moles. So I'm going to take 0.0124 for the volume of the magnesium, and I'm going to multiply that by 0.0123 for the molarity. And so my total excess EDTA is 1.5252. I'm just going to give you all of my digits, times 10 to the negative 4 moles. So the total moles that were reacted with solution are 9.7748 times 10 to the negative 4. So that's the moles of EDTA that reacted with the solution. Now let's move on to the rest of the question. In excess of the reagent 2,3-dimercapto-1-propanol was then added to displace the EDTA from the zinc. Another 29.2 milliliters of magnesium were required for reaction with the liberated EDTA. The magnesium that had to be added is reacting with the EDTA that the zinc let go of. So the moles of magnesium in this case are going to be equal to the moles of EDTA that were let go by zinc. So because this is a one-to-one relationship, that's also going to be equal to the moles of zinc that were in the original solution. So if we take our 0.0292 liters and we multiply that by 0.0123 moles per liter, then what we're going to end up with all of this stoichiometry is that's going to be equivalent to the moles I can't talk and calculate at the same time, 0.0123. That's the equivalent of moles of zinc in the original solution. So I calculate 3.59 times 10 to the negative 4. I didn't give you all of those digits, but there's a 1 and a 6 there. Moles of zinc in the original solution, because that's what this represents. So what is the molarity of nickel in the original solution? Well, how are we going to find that? Well, the moles of nickel in the original solution plus the moles of zinc in the original solution will equal the moles of EDTA that were reacted with in the original solution. So this is the value I need right here. So I'm going to erase the rest of it, just kind of make it a little bit easier to follow. So the moles of EDTA that reacted with the original solution, we're going to have moles of nickel plus moles of zinc will equal the moles of the EDTA that reacted with the original solution. And I have that value of 9.7748 times 10 to the negative 4 moles. And I have the moles of zinc. So moles of nickel are what I don't have. So all I have to do is solve for this one variable. And I get that the moles of nickel in the original solution are 6.1832 times 10 to the negative 4. And again, that is moles of nickel, but that doesn't answer the question. The question asked for the molarities of both the nickel and the zinc. So with the moles of nickel in your calculator, divide that by the sample volume in liters, 0.05, and get that the nickel concentration is 0.012, and I get a 3.6. I would round that to 4. We have 3 significant digits throughout, so I'm going to keep 3 significant digits, capital M molar. So the zinc concentration then I take 3.5916 times 10 to the negative 4, divide that by my original sample volume, 0.05 in liters, and I get a zinc concentration of 0.00718 capital M molar.